To our second main talk of the day, and it is my greatest pleasure to announce that we have Dr. Drew Varnitan. So, Dr. Bar-Natan received his BSc in mathematics at Tel Aviv University in 1984, and then performed his military service as a teacher. He started his studies at Princeton and received his PhD in 87 under Edward Witten. And
No,
is
in
now
91.
Pierce
91. I'm not that smart.
The Pierce Assistant Professorship at Harvard in 91 and 95.
Yeah.
And returned to Israel, became an assistant professor at Hebrew University Jerusalem, and Professor Bar-Natan moved to the University of Toronto starting in 2002. He's written dozens of papers, had 7 PhD students, and his areas of interest include knot theory, finite type invariance, and Kavanagh homology. And it's my pleasure to introduce you.
But now you're underestimating me. I had more than 7 PhD students, even though I can't remember exactly how many. Okay, thank you. Should I start? Okay, so I'll be talking about knots in 3 and 4 dimensions. I actually have 2 motivations. One is to explain fun ways to visualize the 4th dimensions, and that sort of is suitable for actually general audience, people who have not been mathematicians and are horrified by, oh my God, there could be a dimension beyond 4, and beyond 3, sorry. And the second goal is to talk about knot theory, and especially knot theory in 4 dimensions, which is a subject that I've worked on myself and am working on myself. I should say that my talk has a website, http://syr21, and if you'll go there, you'll find various links, including a link down here for a handout. And you may want to have, here's a picture of the handout. You may want to have it in front of you because I will be moving forward and backwards on the slides, and all of them are on the handout at the same time, so you can view even the previous slide when I'm showing the next one. So if you can print it even, I wish you could. You know, if it was a normal talk, I would be printing 100 copies and bringing them with me and distributing them. Unfortunately, I cannot do it right now. So the trick to visualize the 4th dimension is basically to learn how we visualize the 3rd dimension. So our computer screens and books are printed in 2 dimensions, and yet we manage to show 3 dimensions on them. So we know how to go up 1 dimension. So just apply this operation a second time and you learn how to visualize in 4th dimension. That's basically the content of my talk. Maybe I could stop here because there is not much else to add. No, I'll continue anyway. So here's again the handout, and thanks for inviting me. I should have started with that. And you've never been to my lecture room, so here it is. I'm standing in front of this screen right now. The video camera, the webcam is in front of me. It's over there. And there is a nice screen right in front of it where right now I'm seeing, wow, about 20 faces, which is wonderful. 18 actually. So thank you. And if you can, the more of you are on, the better. So let's start. So here's a 3-dimensional object, an elephant. Here's the same object upside down. It was complaining bitterly when I've put him that way to take the picture. And I want to learn how to visualize this 3-dimensional object in 2 dimensions. So the first and least satisfactory way is to project it. Right? You project it, you look at the shadow. Actually, you can recognize that it's an elephant, but you don't see much detail. And in fact, had I given you the shadow, why isn't it scrolling? Had I given you the shadow from above, you might have thought it's a rabbit. And had I given you the shadow from the front, you might have thought it's a butterfly. You wouldn't recognize it as an elephant. So that's a pretty bad way. Here's a better way. So let me call this a thermographic projection. So what I did is I took the elephant and replaced it and placed lots and lots and lots of dots on it, with some gaps in between them so I could see between the dots. And I colored the dots according to their t coordinate, where t stands, so I have x and y coordinate, and a t, I have an x coordinate and a y coordinate, and a t coordinate where t stands for temperature, and if it's hot, then it's red, and it means that T is high, and if it's blue, then it's cold, and so T is small, and I'm calling this the thermographic picture, projection, okay? So here we can see much more detail. So we can see, for example, that the ears of the elephant stick out because there is red here, which means that the one ear is sticking in our direction, sticking out in our direction, and there is also blue here, which means that there is another ear going far away from us. We can also see that this elephant hasn't eaten in a long time because there is nothing in its belly. Because if you look at the belly, you see that there are dots of two different colors, but nothing in between. There is sort of the yellowish and the bluish, and that means, the edge of the stomach, which is of the belly that's near us, and the edge that's far away from us, and there is nothing in between, so it's a starving elephant. I'm sorry. Okay? Likewise, here's the projection from above, and certainly we can see more than a rabbit. So we can see, well, the same shape as before, but we can see the four legs, which, since we're looking from above, they appear to be away from us. So, blue. Okay? And we can see that the tip of the ears, like mine, kind of point up. Okay? And here's another picture. So this is from the back, I suppose. So we can see that it has four legs. 1, 2 in green, 3, 4 in red. We can see that it has tusks facing away from us, so T is small. And I suppose we can see here the trunk in blue, and we can also see the tail in red down in the middle here. Okay, and there is more. So we can also take sections of the elephant. So if I go back to sorry, that will take a little while. If I go back to the elephant as I was standing it in 3D, there is a red plane, a green plane, and a blue plane, and I can move these planes parallel to how they are placed right now. So the blue plane would move this way, the green plane would move in and out, and the red plane would move up and down. And I'll get different sections of the elephant, and the sections are two-dimensional, but using these sections I can reconstruct a three-dimensional view of the elephant. So here's green, here's red, here's blue, and in fact I can turn them into movies. So if you go to the URL that I gave you at the beginning and call it omega, then omega sub g will give you the green movie. Now let's watch it. So let me hit green over here. And here's our movie of moving sections of the elephant. So we can see ear, body, leg, one second set of legs, it's too fast. ear, body, first set of legs, second set of legs, second ear. Well, okay, it went too quickly, but I think you got the principle. And I could do it with the other projections as well. So here is red. So let's play it. What do we see here? Legs, I suppose it's going up, right? So we're seeing, first of all, 4 legs, the tusk and trunk, the body, and eventually only the ears stay. And finally, we could watch it from the blue perspective, and again we will see that the belly is empty. Nothing in the belly. Okay? So all of these are two-dimensional ways to view an elephant. Sorry, I went too fast, too far. All of these are two-dimensional ways of viewing an elephant, and my aim will be to use them to view something in 4 dimensions. What's the thing I want to view? So I want to see knots. So here are knots. Here is a knot. You sort of know what a knot is. You recognize that this is a knot. You can see the picture. You know what it is. You know, formally, well, we'll get to the formally later. But anyway, here is a projection of a knot. And that's not a terribly good perspective, because in fact you cannot reconstruct the knot from just this projection. You cannot tell which strand here is over and which is under. Here is a thermographic projection, and from this you can reconstruct the knot completely. Because you see, now I know that the, well, one strand, I suppose I'll make a line over it right now, is above the other strand, which I've drawn right now, which I've highlighted right now, because its color is red, and red means high temperature, so high T coordinate. And I have this information at all 3 crossings where there was an ambiguity, so I can recover the knot. Why aren't we moving anywhere? Sorry, I don't know why it's refusing to scroll. And here's another way to view knots. So that wasn't an option for elephants, but it's working for knots. It's called a broken curve diagram. So what's a broken curve diagram? It's like the projection, except I left 3 gaps. A gap over here, so a gap over here, a gap over here, and a gap over here. And what does this picture mean? It means everything is embedded in the t equals 0 plane. So we're showing the t equals 0 plane, and everything is in the t equals 0 plane. And at places where there is a gap, what I mean is that the strand actually continues, except it dips down to t is negative. Okay? And I've given you exactly the same information as before. It's still the same knot. And here's the last way of viewing the same knot. So I stand the knot vertically, and I take a gray plane, you can see it here on the left, and I slide it from bottom to top, or maybe it's from top to that bottom, I'm not sure, and I record the sections that I see. Here the knot is colored with various colors. The colors have nothing to do with the depth. I've only made it colored so that you could tell, well, when you look at the section, at any section, the section will be made of a number of dots, and the colors here correspond to the colors here. Okay? So what do we see? So in the lowest section, we see a pair of greenish dots on the right and a pair of purplish dots on the left. And then the greenish dots slightly change their color, but sorry, the rightmost dot slightly changes its color, but as I go up, it remains on the right. So this is this trajectory of dots. The leftmost dot slightly changes its color, but it remains on the left. So this is this trajectory of dots. And the middle two dots, that's where the knottedness comes in, perform an elaborate dance. Okay, so let's see it on video. So, oops, which one was it? I was supposed to memorize. Oh, it's M2, sorry. So this is M2, and here it is. So you can see the two dots stay on the sides, and there is a little bit of a dance of the middle dots. There was a little bit of a dance of the middle dots. And here it is, frame by frame. You know, maybe it was clear enough. I'll just play it again. So we stand the knot vertically, and as the section moves, we see an elaborate dance in the middle. Okay. Are you still with me? Is this okay? Am I speaking too slow? Am I speaking too fast? Good. So let's move on. I know I forgot. I knew I forgot something. I forgot to give credit to the person who made many of the videos that you will see today. This is Esther Dalvit, who used to work with me at the University of Toronto and is, I think, in Italy now. Anyway, so back to the talk. So formally, a knot is a differentiable embedding of S1. So S1 is just a fancy name for a circle into R3. R3, I suppose you know what it is. Except I regard such embedding as equivalent if you can get from one to another by a differentiable deformation that stays within the world of embeddings. So here is a knot. Okay, it's a differential embedding of a circle into R3. You can see the circle, R3 is where I live. And I regard this knot as equivalent to that one because there was a deformation, well, the funny motion that I made, that got from one to the other while staying within the world of differentiable one-to-one embeddings. Okay? The one-to-one plays a role in the fact that I cannot undo it by letting one thing pass through the other, and the continuity, differentiability, plays a role in that I cannot cut it open and then undo it. Okay? Good. So now let's go one dimension up, and here many of the pictures are due to Carter and Saito. Banach is just standing in the middle, photobombed us. And formally, a two-dimensional knot in R4 is exactly the same definition. So a differentiable embedding of S2. So S2 is the two-dimensional ball into R4. Well, what's R4? I'm not sure how to draw it. It's that space that has four axes, and we just learned, or we're in the process of learning how to visualize it. Modulo differentiable deformations of such, and perhaps I should give some examples. So here is a first example due to Carter and Saito. this is a two-dimensional knot in R4 presented using a broken surface diagram, and you should think of it as the analog of a broken curve diagram. So what we see here is a two-dimensional surface in R3. I am thinking of it as the R3 which lies inside R4 at t equals 0. But this surface has some gaps in it, some breaks. So there is a gap over here, for example. Okay? And you know, here there is a whole, not disc, annulus, a whole ring missing. Wherever there is a gap in the surface, it means the same as in the case of broken curve diagrams. It means that the t-coordinate dips down to below 0. So for a moment we don't see the surface, but because we're only looking at t equals 0. Okay? So this is a surface in R3. I'm thinking of it as lying inside R4, and the gaps means that I actually dip down into the fourth dimension. Okay? Now, what surface is it? It looks like a complete mess. Let's try to digest it. So, let's try to digest it where it's easy. Over here, I see a little piece of a tube. So, let me draw it like that. Here is this little piece of tube. Now, let me move to the right from this point. Tube, 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 tube bends. Well, okay, if a tube bends, it's still a tube, right? If a tube bends, it's still a tube. Tube turns left, so it's still a tube. It just continues as a tube. From the perspective of the domain space of this map, right? This represents a map from, well, from some surface into R4. So from the perspective of the domain space, so far I've only seen a tube. Okay? Now, the tube has a gap, which really means that it dips down over here, right here. It dips down, and if I were to look up in the t-coordinate, I would see something above me, right? If I was walking on the tube. Okay? But it's still a tube, so the tube continues. Then it suddenly explodes. It becomes wide. So really it becomes a drum, a big thick drum over here. You can see this big thick drum, right? And as it explodes, it goes over something because something else passes through the same place but has a gap in it. So now if I was standing on the top of the drum, so if I was standing, if I was standing here on the drum and looking down, I would see that there is something below me, down in the t-coordinate. Okay? But it's still a drum, so a drum is perhaps a thicker tube, but it's still a tube, okay? And then the drum closes on the other end with a gap, so I pass under something. If I were to look up, I'd see it. This is this gap here. Okay? But then but anyway, it closes. So that's what I've seen, going from here to the right. Now going from here to the left, let's see what we see. Okay? Let's check what we see. So going to the left, I see tube, 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 tube bends, tube goes over something because there is something there which has a gap. So I look down and I see that I passed another piece of surface. Again, down in the t-coordinate. Tube opens up like a fountain, or like, I don't know how to quite explain it, but it opens up and becomes a drum that wraps back on itself, right? This is this big drum here. So tube, well, turns, I will not bother to show it, and then it becomes a lot thicker. This is this whole drum over here, and out from the side of the drum, another tube comes out. Sorry, maybe I should try to make the picture below not interact with the picture above. So this becomes a big drum, and out from the side of the drum, another tunnel comes out. This tunnel, oh, by the way, the drum goes under something. If I had, before when I passed over something, if I had marked it, I would see the marking. Okay, it's the same place where I've been before. But anyway, out of the drum comes a big tunnel. The tunnel goes over something in the four-dimensional sense, and it's something where I've been before. It's actually over something which is on this end. And then it goes under something, again I've been there before, and then it closes up while going over something, again something where I've been before. So overall it just closes up. So the domain space is a long tube that's capped on both ends, and that's just a sphere. So so this picture really described a map from S2 to R4, so a sphere inside the four-dimensional space. So that's a two-dimensional knot. Are you with me? Okay, next picture. Here's another one. I could go through it in a similar way, and you would see that this messy surface, which is also due to Carter and Saito, is again representing a two-dimensional sphere inside R4. But this one is stupid. Sorry. Why is it stupid? So let's look at it more carefully. So over here, the vertical part of the tube passes over the horizontal part. You see, because in the horizontal part you can see two cuts. So it means that the horizontal part dips down in the fourth dimension. So this thing goes over, but it goes over on both sides of that tube. So I could simply pull it out and undo this whole bend. So this whole bend here is a waste, is unnecessary. I could deform it to a straight tube going from here to here. Similarly, over here, I could disconnect these two tubes from each other, make one pass completely behind the other, and then this part could be pulled aside, and well, likewise you can just continue searching through it and you can find that you can undo everything, and even though this is a fancy picture, you can deform it within the world of one-to-one functions, within the world of embedding. You can deform it into the unknotted circle. So, well, I wouldn't call, maybe it's not silly, but it's the unknot. It's what we would call the unknot. Are you still with me? Good. So, let's continue. Oh, here are two more pictures. So in fact, it's one picture. So this is a thermographic projection of a sphere. So the colors represent the t-coordinate, except over on the left, you cannot see, you know, part of the surface is hiding other parts. So I've cut it in half, and here you're seeing only half of the picture. And it's easier to look at just the one half, but this half really stands for a half of that. I mean, this isn't the knot. The knot is here, okay? Anyway, so let's look at the one half. First of all, this is clearly a sphere. Why? Because if I look at it, this part is a tube. The tube continues on one end and gets capped, continues in the other direction and gets capped, so it's doubly capped tube, and a tube which is capped on both ends is a sphere. So that's a sphere. Is it knotted? Well, let's think about it. Had the whole tunnel in the middle been red, it's not all red, right? It goes red, it goes through the spectrum, becomes blue, goes and turns back red again. But had it been red throughout, it would mean that its t-coordinate is always higher than the t-coordinates of the caps, this cap and that cap, which are both green. So I could pull this cap out. It's really under, it's not touching the red tunnel. So I could pull it out, and I could pull that one out, and then I'd get the whole thing completely disconnected, and it would be an ordinary sphere. However, that's not the case. So we flow from red to blue, and it means that at some point along the way, we will have over here the exact same shade of green as here. Which means that if we actually try to pull the cap out, again, so I'm sort of using the intermediate value theorem, at some point I will have the precise same color, and when I pull it out, I'll have the precise same color at the precise same place, which would mean that this is no longer an embedding, it's no longer one-to-one. So it's the parallel of trying to have a piece of string cut through itself, which is forbidden. So this seems to be knotted. But of course I didn't prove that it's knotted, because maybe there is a different way to unknot it. I've failed to do it in one way, but maybe there are different ways to do it. Okay, so let's look into that. Okay, so, sorry, before looking into that, here's the same picture once again, but as a broken surface diagram. So you can tell it's the same, right? We have the tunnel, and we have, it's kind of, so the tunnel, I suppose, maybe starts, let's say starts here and goes all the way to here, but then it's capped on this end, and it's capped on that end. The caps go over the main part of the tunnel, and you can check that, like here it goes, the tunnel is above the cap, because you can see the cut in the cap, which would mean in the previous notations that the tunnel is red and the cap is a less red color. Okay, so it's the same picture as before. Anyway, oh, and again, before going to back to the question, is it really knotted? I want to give a few more examples. So you see, ordinary knot theory in 3 dimensions, in some sense, is made out one ingredient, namely a crossing, and then you repeat this ingredient. So if you want to draw a trefoil knot, you take 3 crossings and connect them with each other. So partially, not fully, you can do the same in R3, in R4, sorry, for 2-dimensional knots in 4-dimensional space. So I want to show you a few basic ingredients that appear in 2-dimensional knot theory. So the first ingredient, it's kind of funny. The notation for it is the same notation as for ordinary crossings for 1-dimensional knots in R3, but that notation over here actually stands for something else. It represents a pair of tubes where one tube is thicker than the other, so the tube whose symbol is the overline is thicker than the tube which is represented by the underline, and where they intersect, the thin tube goes first over, well, it has to cross from one side of the blue tube to the other side. So here the colors are not thermographic, the colors are just so that I can refer to them. So the red tube has to cross the blue tube. The blue tube has two sides, so when it enters from above, because you can see that there is a cut in the blue tube, and when it exits from below, so because you can see that there is a cut in the red tube. So I could show you a movie representing this, but perhaps I'll skip it because I hope it's clear enough. But let me also show it as as several frames of a movie. So basically, if I were to take sections of this, going from the bottom to the top, then at the bottom I'd see two circles, right? Each tube will be two circles. So I'd have two circles in R3. The two circles are flying in towards each other. One is passing through the other, and then they come out on the other side. So one is flying, passing through the other, and they come out on the other side. That's this ingredient. So here's a video that I don't need to show you, but I feel I must. It is showing, well, I'll go back to here. I don't know if you can really see. It's showing a diver at the bottom of a pool, lying on their back and doing funny thing. So let's see, funny things. So let's see what are these funny things. Click Bob, and here it is. So it's a YouTube video. Here's the diver. It's blowing toroidal air bubbles, and the toroidal air bubbles flow through each other and then back again. So this diver might have thought he was playing a funny game, but in fact they were demonstrating to us knotedness in 4 dimensions. Okay? You can find this on YouTube. By the way, you can even find videos of dolphins doing this. I never knew you could blow toroidal bubbles, but ring bubbles. But you know, if you Google double ring bubbles or something like that, you'll find these pictures. Okay. Any questions, any comments before I go back? Okay, so that was one ingredient. But there is another one. The other one is indicated by a crossing over here, by a crossing in which I didn't indicate an upside or a downside. And what it stands for is two rings flying or trading places, but not by flying one through the other, but just by flying side by side. And all ways of flying side by side are equivalent. So, you know, I could fly this way, or fly that way, or fly from above, or fly from below, and they're all equivalent. You can deform each one to each other, because like if basically, you know, a way for two rings to change position externally can be specified all I need to tell you is what is the direction vector from orange to blue when I'm in the middle of the transverse. So this direction vector will be a vector, here's a ruler, it's a vector from orange into blue, and this vector is some vector, you can basically rotate this vector always, all possible positions for this vector are related to each other by rotation, and these rotations correspond to deformations of the four-dimensional picture that these movies represent. And maybe the last bit, so now I can assemble these pictures. So if you look down on the bottom right, so here is a picture that has 3 tubes in it. So by the way, if I wanted to get a two-dimensional knot, I would have to continue this picture. So, you know, just like a crossing in two dimension in ordinary knot theory is not the whole knot is assembled from several crossings. Similarly, here I'm not drawing the whole knot, I'm drawing a part of the knot, and that part of the knot is made of 3 tubes, red, yellow, and blue, and these red, yellow, and blue tubes dance, and if I were to view it from the bottom to the top, the dance is yellow go through red, then blue and yellow trade places externally, and then red goes through blue. So maybe this one is worth watching, so let's again go to the video launcher and launch video F. Here's the picture. Yellow through red, yellow and blue trade places externally, and then red passes through yellow, and that was a four-dimensional piece of a knot, not the whole knot. Here's the same picture as a broken surface diagram. And thank you, Esther Dalvit, for making this video. Are you with me still? Okay, good. So, on we go. But here is my trefoil knot. This knot is, by the way, called the trefoil knot. How do I know that it's actually knotted? Even for ordinary knots in R3, it's a non-obvious question, right? Because you see, here are a few horrible examples. So here is Shireen's knot, here is Thistlethwaite's knot, and here is Haken's knot. Let's look at Shireen's knot. There is a video for it. So it's the video U. Let me click at U, and here's the picture. So here is the Shireen picture, and let's start deforming it, or in fact, let's let YouTube or Shireen deform it for us. It's hard to tell what it is. It could have been anything. At some point, perhaps now it's becoming clear that it's actually the knot. But in the beginning, well, okay, I think now it's perfectly clear that it's the knot. But in the beginning, it certainly wasn't clear. Right? So, you know, if I'll go to the beginning back again, you could look at this for half an hour and you wouldn't be able to tell if it's knotted or not. Okay? So why am I showing you this? I'm showing you this because to demonstrate the necessity of proving things. You see, how do I know that there isn't some, just like there was a crazy way of relaxing this to the knot, maybe there is a crazy way of relaxing it to the picture I had before, to the trefoil knot. So then I would unrelax it from the trefoil to the crazy Thistlethwaite picture or the crazy Haken picture, and then relax it back again to the anode. How do I know that they're not equivalent? So that requires a proof, and let's start working on it. So the first step is to turn it into a combinatorial problem. So you see, the way I defined knot theory, the definition is sort of analytical. Maybe it belongs to analysis. Maybe it belongs to differential geometry. Maybe there is no difference between the two, right? Because I said it's an embedding of a smooth map from the circle into the R3 with modulo deformations of such. That sounds like analysis, okay? But then comes Reidemeister's theorem, which converts it into combinatorics. So the theorem says every knot can be represented by a broken curve diagram. So it's made only by curves and by the basic ingredient, so namely by crossings like the crossing indicated here. And even better, any two knot diagrams, by this I mean broken curve diagrams, represent the same three-dimensional knot if and only if they differ by a sequence of Reidemeister 1 or Reidemeister 2 or Reidemeister 3 moves. So it is obvious that each of these moves is actually, so the two sides of each of these moves correspond to the same knot, right? If you have a kink in a knot, so here is a piece of a knot and it has a kink, I can pull it and I'll get a straight line. Sorry, it was out of your vision perhaps, okay? So three-dimensionally, these two broken curve diagrams represent the same thing. The second one is even easier. You can slide the top one to the left and I don't know. You can slide this one to the left and that one to the right, and it's clear that the two sides are the same. Reidemeister 3 move is also easy. Perhaps it's not drawn in the best way here. Maybe I'll draw it slightly better. Really what I'm saying is that if you have a crossing and a third strand going underneath, going under in two senses, both in the vertical sense and in the 3D sense, then that's equivalent to the same crossing and that extra strand going above. So basically slide that extra strand. Take that extra strand and slide it up while keeping it under, behind. Okay? So it's clear that these three moves represent the same three-dimensional picture. And after, and Reidemeister's theorem says that that's all there is. So if two broken curve diagrams represent the same knot, then they differ by these moves. So I'll skip the philosophy that's down here and tell you how I use it to prove that the trefoil is not equal to the unknot. So what I do is I define an invariant. An invariant is an easily computable quantity, number, polynomial, matrix, quantity that you can compute from a broken curve diagram and which does not change if you make Reidemeister moves. If you had such an invariant, let's call it lambda. So if lambda was such an invariant, and you computed it on the unknot and you got 3, and you computed it on the trefoil knot and you got 9, then you know that the unknot and the trefoil are not the same because, again, it doesn't change when you do Reidemeister moves. So if they were the same, the value would not change as you do a long sequence of Reidemeister moves. So you would get that the value on the unknot and the value on the trefoil are the same, but they are different. So they cannot be the same. So I have to define such a lambda. And here's the definition. I'm running out of time. What should I do? I would prefer to speak for another 5 minutes, right? But the bosses should tell me. Can I? Okay, sure. So here's a definition of one such invariant lambda. So basically, you count the number of legal colorings of the broken surface diagram. What's a legal coloring? A legal coloring is a coloring in which you color every arc in the broken curve diagram with a color. So an arc is an unbroken piece of curve. Okay? So here there are 3 unbroken pieces of curve, and I could color them red, green, and blue, for example. Legal, so I will call such coloring legal if at every crossing, so every crossing is either monochromatic, so the whole crossing is the same color, or the 3 colors appear in it. But a crossing is illegal, a coloring is illegal if exactly 2 colors appear in that crossing. So the crossing on the right is illegal and these 2 are legal. So clearly, lambda of a circle is 3 because the whole circle is one curve, so you can color it either red or green or blue, so it has to be 3. You can check that lambda of a trefoil is 9. So basically, if the picture was this, I could color the first arc red, I could color the second arc blue, so these 2 I could choose arbitrarily, any way would work, but whichever you choose for these 2, the third one, by this coloring law, is forced to be the third color. So in this case, the third one is forced to be green. So I basically have 3 choices for the first, 3 choices for the second, overall 9 choices, and since 9 is not equal to 3, I've nearly proven that the trefoil is different from the unknot. Why is it only nearly? Because I still have to show that this is an invariant. I have to show that when I do Reidemeister moves, nothing changes. The number of colorings does not change. So that's happening in the next slide, and it's only a sketch. So all you have to check is that if you have the left-hand side and the right-hand side of a Reidemeister move, and their ends are colored the same way, then there is a bijection, there is a single way to continue the coloring into the internals. And you can check it in each of these cases. So basically, if you've colored the right-hand side of the Reidemeister 2 move, there is a unique way to correspondingly color the left-hand side. So the number of colorings of the right-hand side, there is basically a bijection between the colorings of the left-hand side and the right-hand side. The bijection is essentially shown in this picture, and therefore the number of colorings is the same. Likewise for Reidemeister 3. Okay? Good, but that was the old knot theory. Now what about one dimension up? So now I'm really running out of time, so I'll have to do it really quick. So first of all, there is a theorem, much like Reidemeister's theorem, which says that every 2 knot can be represented by a broken surface diagram, and there are only 3 basic ingredients. Basically, you project the knot into R3, it's in R4, but you project it into R3, so you get a surface in R3, and then you can either have two parts of this surface intersect each other, except it's a broken intersection, so in fact in the t-coordinate, one side is above the other, or in fact you can have three pieces of surface intersect at like the coordinate axes, like the coordinate planes in R3, but again this is a broken surface intersection, so in 4 dimensions there is no intersection here because red is higher than green, which is higher than blue. Or there is one further funny configuration called a branch point, and I wish I could explain it, but I don't have the time. And then there is, instead of a Reidemeister theorem, there is a Rosemann theorem, and Rosemann is an active mathematician in Iowa, and Rosemann says any two broken surface representations of the same knot differ by a sequence of Rosemann moves, and instead of 3 there are 7 of them, and here they are, but I cannot go through and explain in details what they are, but well, you can stare and look and possibly see something. And then there are 3 colorings in 4 dimensions. So you color unbroken patches of the surface, and the rule is that at every intersection line, either one color appears or all 3 colors appear, like here. And then that makes, like triple intersections, there are several possibilities how to color them, and they're all shown here. And in fact, the branch points have to be uniformly colored. And then you can check that the unknot, well, the elephant is actually an unknotted balloon, right? So the elephant has 3 colorings, the funny knot that I was showing has 9, and so they're different, provided I show invariance. To show invariance, I have to go through, sorry, I don't know why this is showing. To show invariance, I have to go through the Rosemann move and check how they are colored. And of course, I'm already out of time, so I will not show you. But let me just say that there is much more to knot theory than that. So for example, the knot table is much greater than just the trefoil and the unknot. And the invariant we found is actually quite weak. So we have to find better ones. And, you know, in Dreamland, I would have told you that there is a better one. It's called the fundamental group. There is a whole group that you can construct out of a knot. And in fact, also out of a 2-dimensional knot in R4. But, you know, it's actually fair that the last minute of a talk will be just a review of what I couldn't do. So that's what I'm doing right now. And finally, I would tell you that perhaps the simplest open problem in knot theory is right here. So namely, there is a specific type of 2-dimensional knots in R4 that has a specific way of representing them, and there is a sequence of Reidemeister moves between them, but nobody knows if this collection of Reidemeister moves is complete or not. So in principle, if I had another 20 minutes, I could tell you about the simplest open problem in the question, in the problem. If you want, in the subject. If you want to read more, that's where you could find it, and I'm done. And I'm 2 minutes ahead of the formal end of the lecture and 8 minutes behind the time when I was supposed to allow for questions. So ask questions. Any questions?
So this, it's Graham. This list of Rosemann moves, there are more obviously than the Reidemeister moves. Are there guesses about, you know, embedding 3 manifolds in 5 space, and that there are still more moves? Are there work in this direction?
I actually don't know. I think it's not known. I think it gets too complicated, and maybe it's known a little bit beyond. It's definitely not known in general. Like, so if you ask about k in n, I don't think you can make a finite list like that, though I'm not 100% sure. Stefan, maybe you know?
I'd just like to say, I don't think we have, unfortunately, I think we're out of time to get to the scheduled talks.
Oh,
Thank you very much
I'm
for-
sorry.
for your
Okay.
talk today, Professor Bar-Natan. Maybe people can corner you in the coffee breakout room if you have time, or
I'll stay around. Thank you.
thank you very much for speaking today. So we have our seventh set of parallel talks starting in just a moment. So